Hello, hello, welcome back to another weekly exam problem. This week we're going to be looking at an exam 1 problem that comes from NHT 2023, exam 1. So that means it's a tech-free question. We are not allowed to use our calculators. So this question is asking us to consider a particular function. In this case, it is a logarithm function, and we want to find the implied domain of that function. So before we answer this question, we need to consider what is the implied domain of y equals log e of u. So what is the implied domain of this function? To understand that, let's just remind ourselves of what a logarithm looks like. So I've sketched here a graph of y equals e to the power of x. Okay, so this is an exponential function. Now, when x is equal to 0, we get here e to the power of 0, which is equal to 1, which gives us this coordinate right here. Now, when x is equal to, say, 1, we're going to put x equals 1 into this equation. E to the power of 1 is equal to e, which gives us e, which is 2.718. So what's written there. If e was equal to negative 1, if x is equal to negative 1, we're going to get e to the power of negative 1, which is the same as 1 over e. And 1 over e happens to be equal to this number right here. Now, as we can see, as that number gets increasingly small, say it was like, 4. If we put in 4 here, we get e to the power of negative 4, which is 1 over e to the power of positive 4, which is a small number. It says it's 0. It's not actually 0, so there we go. That's the value. So it's negative 4, that positive number there. And as we can see, does not matter how small this x value gets. We could be down at negative 100, and we would be so close to 0. It even thinks it's 0. Which is kind of hilarious. But it's not equal to 0. It's just getting really close to 0. So that's an asymptote, right? Like 1 over 1 million is extremely close to 0. Looks like Desmos only goes down to, there we go, it's funny. That's the cutoff before it just says, okay, it's close enough to 0. It is close enough to 0, but it's not 0, right? Like 1 over a billion is like 0.00009 zeros, 1, 8 zeros, 1. Regardless, it is really close to 0. It is not 0. Okay, that's the first thing, which means there's this asymptote at y equals 0. And of course, the graph of y equals natural logarithm, which is log base e of x, is just the inverse of that equation, which means it's like we've taken that graph there and we've reflected it along the line y equals x. Why is that? Well, the reason is I'll go back to my screen over here. We're taking y equals e to the power of x. The inverse means we swap the x and the y around. So this becomes x equals e to the power of y. And then we're rearranging to make y the subject. And as we know, based on the definition of a logarithm, another way of writing the statement is to say y equals log e of x. So they are inverse equations of one another, as we can see there. And that gives us this relationship. So essentially all that boils down to is that we have a vertical asymptote for the logarithm graph at x equals 0, which means that a logarithm is only defined for x values that are strictly greater than 0. So you must be strictly greater than 0, not greater than or equal to 0. If you did that, you would have definitely lost the mark here, or you'd have lost at least 1 mark for doing that. All right, so we know that's the domain of a logarithm. What about this thing that is inside the logarithm? Well, if we know that the domain of f is going to be defined when that thing is greater than 0, we need to think, when is that thing inside there greater than 0? So we need to consider 3 plus 2x minus x squared. When is it greater than 0? So this here is a quadratic. So let's consider the quadratic, right? This is a quadratic which has a negative x squared term. So because the x squared term, I'll write it in descending power order. Because that x squared term is negative, that means it's going to be like a sad face parabola. It's concave down. Okay. So when that, like let's say the graph looks like this. When the value of y is less than 0, the function is going to be undefined. Because this thing here, if that's less than 0, then we put it into the logarithm. We have something less than 0 inside the logarithm. We have a problem. If it's equal to 0, we've also got a problem. So it has to be something that is strictly larger than 0. So let's try and figure out what are those x-intercepts, because if we can find what they are, we know when this function is like above the line, when the y value is greater than 0, or like the output of this function here is greater than 0, they're the acceptable values of x. So to do that, we need to start by trying to factorize this. Now, this is not a monic quadratic. It's easy to factorize quadratics when they are monic. So I'm just going to go ahead and factor out the -1. So I'm going to take out the -1 term here, which means I get brackets here. Now, when I take out the negative term, that means I'm going to divide everything by -1. I'm taking it out because I want to make this a monic, right? I want to make that x squared. Okay, so let's try and do that. I'm going to go ahead and this number, negative x squared divided by -1 gives us x squared. 2x divided by -1 gives us -2x. And then 3 divided by -1 gives us -3. That's what we get, right? We want to figure out when is this greater than 0? Well, that there is a simple quadratic. We have x squared minus 2x minus 3. What are two numbers that add to make -2 and multiply to make -3? Well, that would be -3 and 1. So that's how this looks factorized. Now, when will that occur? Well, when will this expression be larger than 0? As we can see looking at the graph, it will be larger than 0 between these two x-intercepts. Now, the smaller of those x-intercepts is going to be -1. The larger is going to be 3, because by the null factor law, this is equal to 0 when x equals 3, because we'll get 3 minus 3 equals 0. This is equal to 0 when x equals -1. We get -1 plus 1 equals 0. So we can see here that the values of x must be less than 3 and greater than -1. So that is the implied domain of f. Implied domain of f. Okay? Moving on, stating the x-coordinate of the local maximum of f of x. So let's have a think about this, right? This little graph inside of our function, that is going to have a maximum value at a particular point. So whatever that maximum value is, that's also going to be the maximum value of this log base e expression, now f of x expression. Now, that might seem a bit hand-wavy. I know it is. Later on, when we get up to calculus, you'll have a way of actually proving this by calculating the derivative and working out when that's equal to 0. For now, it's enough to sort of speculate. Like, most likely the maximum of this function is going to occur when that quadratic term is at its maximum. So let's consider, when is -3, or when is that quadratic term, x minus 3, x plus 1, which is the same as -x squared plus 2x plus 3, when is that a maximum? So if we consider our graph, we can see we have two x-intercepts, one at -1 and one at 3, right? And what we should remember is that quadratics, parabolas, they are symmetrical, which means that the turning point occurs right in the middle of those two values. So we can say that the maximum will occur at the points where x is equal to the average of those two values. So -1 plus 3 divided by 2. Now the number that's right in the middle of those two numbers is -1 plus 3 is 2. 2 divided by 2 is 1. It's equal to 1. Okay, that's the answer. It's a B. So we found the x-coordinate of the local maximum of f of x is equal to 1. Now we just need to figure out what are the values of x when f of x is equal to 0. So that's the answer there. Now f of x, we can see from up here, is equal to log e of all of that stuff. So let me write that out. Log e 3 plus 2x minus x squared. Now we want to know, when does f of x equal 0? So let's just go ahead and replace that with 0. This is what we're trying to solve. We're looking for values, so we should probably get more than one value. There's usually a little hint in these questions. So let's go about trying to solve this. If you're trying to solve a logarithmic equation like this, you typically want to try and manipulate it. You can convert between exponential and logarithm form just to try and simplify the problem down a little bit. So here, one strategy that you might use might be to write it in exponent form. Another way of writing this same statement is e to the power of 0 is equal to 3 plus 2x minus x squared. Now, e to the power of 0 is actually just equal to 1. So we get this equation, which is a quadratic equation. And the way that we typically solve a quadratic equation is step 1, rearrange it to make one side equal 0. Step 2, apply the quadratic formula or completing the square to try and figure out what x is equal to. So let's go ahead and do that. I'm going to bring everything over to, well, it doesn't really matter which side I bring it over to. I'll bring it all over to the right-hand side. I'm just going to minus 1 from both sides. If I minus 1 from both sides, that gives me e equals negative 2x plus 2x plus 2, okay? That's my expression. And we know that the quadratic formula is negative b plus or minus the square root of b squared minus 4ac over 2a. So I can just go ahead and substitute in those values. From what we've worked out here, a is the coefficient of x squared, which is negative 1, b is the coefficient of x, which is 2, and c is the constant, which is also 2. So going on ahead here and substituting those values into the expression, we're going to get negative b, which is negative 2, plus or minus the square root of b squared, which gives us 4 minus 4 times negative 1 times positive 2, okay? All divided by 2 times negative 1. All right, now simplifying that one down, we're going to get negative 2 plus or minus the square root of 4. Now, this is a double negative here, right? This is 4 times negative 1. So that makes plus 4. And then we times that by 2. So that's going to give us 8 in there. We're dividing that by negative 2. Simplifying that down a little bit further, that's going to give us negative 2 plus or minus that now. That third there is just equal to 12. So we get negative 2 plus or minus the square root of 12, all divided by negative 2. And then we need to further try and simplify that. We know, based on our knowledge of surds, that the square root of 2 is actually the same as the square root of 4 times 3. Because 12 is equal to 4 times 3. We could represent that as root 4 times root 3, and root 4 is just equal to 2. So this is 2 root 3. So coming back to what I was writing over here, this is equal to negative 2, actually I'll do it over here, just so I don't run out of space. Negative 2 plus or minus 2 root 3 over negative 2. All right, now let's try and deal with those negatives. If we think about this denominator here, sort of like there's a common factor of negative 2, if you think about it. If we take out that common factor of negative 2, we have 1, well, if this is plus, like plus 2 root 2, I divide that by negative 2, I'm going to get minus 2 root 2. So this is like minus plus. If it's plus, it becomes negative. If it's negative, it becomes positive. 2 root 3. And that's being divided by negative 2. Now, there's a common factor in the numerator and the denominator of negative 2, so I just divide that out, cancels, and we get a final answer of 1. I guess it doesn't really matter if we write plus or minus or plus, but let's just write out the answers. 1 minus 2 root 2, 2 root 3, and 1 plus 2 root 3. And those are our solutions for the values of x for which the function is equal to 0. And just to have a look at this, just because it's a bit of fun, if we want to sketch to see what this overall graph would look like, we could go ahead and type it into Desmos. So let's just imagine, what does this graph look like? That is y equals the natural logarithm of 3 plus 2x minus x squared. You can see it does look like this little upside down parabola. The maximum does occur at x equals 1, and you can verify for yourself that these points are x equals 1 plus the square root of, 2 root 3? No, root 3, yeah. 1 plus root 3, and x equals 1 minus root 3. There they are. So you can see that those are the values of x for which the function is equal to 0, and that the maximum does indeed occur at 1. And going back to question 1, there are indeed there are indeed asymptotes at x equals -1 and x equals 3, which were the values for which that quadratic was equal to 0. All right, so that is the solutions to the weekly exam question for this week. Hope you guys enjoyed that one. Good luck getting through the rest of the exercise. And if you have any questions, feel free to send me an email. All right, see you guys next week. Have a good weekend.